Hi there, welcome to your probability lesson on Venn diagrams. Today we will focus specifically on union and intersection. Here's union, here's intersection. To begin, we've looked at several different ways to diagram in probability. The simplest way to diagram a sample space is called a sample space diagram. Here's an example. It's a useful way to represent when we have particularly two events happening. So here we are rolling one die, a four-sided die, and here we're rolling a six-sided die. So we have a two-dimensional table and we can fill in the results or the sum of all the scores on the dice. So this is, again, sample space diagram clearly shows us the full set of outcomes. We can see them here, but it's only useful when we have two axes. All right, another way to represent probability is through probability tree diagrams, which also is another way to show possible events. For example, one thing happens, we have three different outcomes. So that's the first event. It happens and there's three outcomes. And we can see the probabilities are shown along the path. And then after that, another event happens. So it says second event. And there's three different outcomes for that event as well. As you know in tree diagrams, when we want to follow one path, so outcome one and outcome one again, we just multiply the probabilities along that path. So that's what it says here, multiply along the branches. In the end, when we have all these paths, all the paths are all the possible outcomes in total. Therefore, all these probabilities should have a total of 1. So you can add any pairs or threes of these and find out the probability of those three paths and so on. Another way to represent probability is through Venn diagrams, and that's what we will concentrate on today. Usually a Venn diagram will have a rectangle. This one does not, but there's usually a rectangle around it. Here we have an example where we have characteristics of whales and fish, and then there's an overlap. And those are the characteristics that both whales and fish have. So again, today, let's concentrate on Venn diagrams. Let's begin with complementary events. We have this great photo here. Enjoy that. All right, now the situation is we have 14 students who play basketball in a class of 23. So the rectangle will represent the entire class, or what we call the universal set. So we use the letter U, 23 students. Within that rectangle of all the students, we have this group here, this set, and I'm going to call it set B, and those are going to be the students that play basketball, and we have 14 of them. Okay, great. That's a basic Venn diagram. There's only one set within this universal set. Now see if you can find these values here. Let's do part B first. Okay, hopefully you notice if there's 23 here, 14 here, there must be 9 students that don't play basketball. So in the universal set, the number of students we have is 23. The basketball players is 14. And the B naught, that's what a complementary event is. That B naught means that symbol there means the things that are not B, and those are the 9. So hopefully you came up with the 9 as well. Now let's try this question. Okay, in this one, to find probability, remember that n of something just means the count, but probability means the count of those things divided by how many are in the universal set. So for probability of B, if we were to randomly select a student, we have 14 students out of the 23. So notice like here we just had NB, but here we have probability, which is NB over the universal amount. And the probability of choosing a student that is not a basketball player, so outside of the B circle, we have 9 out of 23. Okay, so complements. Complement of an outcome is when the outcome does not occur. So here we have probability of something occurring, and here's the probability of it not occurring. And in a diagram form, it can be shown clearly like this. We have all this is set A, but outside of that, the shaded zone in green is not A. So all the things outside of A are here, still within the universal rectangle. So as we can see, by taking probability of this event plus the probability of it not happening, I know we're using E here and this is A, but I think you can see the connection. This probability plus the probability outside of it makes a 1 because that captures all the possible events within this rectangle. If you rearrange this, you can say the probability of not E is 1 minus probability of E. For example, if there's a probability of 0.6 of A happening, then the probability of A not happening is 0.4. Okay, complementary events are useful in examples such as this. We have a bag with 4 blue stones, 3 green, 5 red. 1 is randomly selected. What's the probability a stone will not be blue? Let's see if you can answer that first. And now let's look at 2 approaches to solve that. First approach is we say probability of not blue. Well, then it's all the green things plus all the red things. So the probability of green is 3 stones out of 12. Probability of a red stone is 5 stones out of 12. And that means probability of not blue is, add those two up, 8 out of 12. And that makes sense because 3 plus 5, 8 stones out of the 12 are not blue. But using complementary events is probably a better way, not in this case necessarily, but often it's a more efficient way to deal with probability. So not blue is the same as saying 1 minus it is blue, right? So probability of not blue is 1 minus probability of blue, which is 1 minus, and the blue ones are 4, so 1 minus 4/12. And now in a simpler calculation, I mean this was simple because there's only 2 things to add, but let's say there was many more. This calculation is very simple. We can just subtract and we get the same answer. So make sure you understand that simple idea, but an important one. Okay, moving on. Let's say we have these ideas of intersection and union that I want to talk to you about. So again, we have 14 students, 23 students, 14 play basketball, and additionally 7 play volleyball. So here I'm going to make another circle, 7 play volleyball, and 6 play neither. Notice I put these 2 circles or sets to overlap because there might be students that play both basketball and volleyball, but we don't know yet. Let's check. So here's the Venn diagram for that. 6 play neither, so I'm going to put the 6 out here. And now, what is the intersection? And so that you know, this intersection is this part in the middle where both occur, so where students play basketball and volleyball. So what do you think? Okay, so intersection here is 4, and the place that number comes from is this. We know there's 23 in the class. 6 do not play these sports, so 23 minus 6 is 17. So we know there must be 17 students within these circles. And then, however, when we add the 14 and 7, we get 21. But we know this must be 17, so we're 4 above what it should be, and that always gives us the intersection amount. So there's the 4. Now that we know there's 4 there, we know there's 10 here, because that together makes 14, and if we know there's 4 and 7 here, then that must be 3, because that makes 7 together. Alright, so the intersection probability, and there's the symbol for it, intersection looks like this, is number of things in the intersection over the number of things in the universal set. So 4 things, 4 students that play basketball and volleyball out of the 23. Try the same thing for union. Union, let me explain what it is. It's B or V. It basically means they play basketball, or they play volleyball, or they play both basketball and volleyball. So let's see what you get. Okay, so if you tried that one, the union symbol, by the way, looks like this. And in that case, how many things are in the union? Well, I just explained the union means everything. The B things, the V things, or both of them together. It means the combination of all those things there. So the total number there is 17, and 17 out of 23 is our probability. Okay, so just to summarize, a complement is denoted like this. A complement of M is M naught with the low symbol there. It means the things that are outside of M. So here's M, and then M naught is outside there. An intersection is noted like this with this symbol here for intersection. It means both M and N. So in this diagram, this is your intersection. It's where both occur. A union is shown using this symbol, looks like a U, and it means things that are in either M or N or both. That both part is important. So here, things that are in M or N or both. So union is all that. Okay, great. Let's try another one. See if you can set a Venn diagram. Well, I'll help you with the first one. You roll a 6-sided die. Event A represents you roll a 1 or 2. Event B represents a roll of a 5. So here is my Venn diagram. Here is a 1 or 2 being rolled. That's event A. Here's event B. I roll a 5. That means what are the other possible rolls that are not captured here? Well, they are rolling a 3, 4, 6. So they go out here. Now find these probabilities. Okay, check your work. Yep, we have 2 things in that set, 1 thing in that set, and 3 things in the union. That's 1, 2, 3. All those things are the union of those 2. Next, try this one. Set up the Venn diagram and see if you can answer those. Okay, so here we go. There's the Venn diagram. This time there's an overlap because a 2 is both an even number and a roll of a 1 or 2. So here's a roll of 1 or 2. Here's the even numbers. There's the overlap. There's the remaining. These answers then are these values here. Check your work carefully. Okay. These, by the way, are called mutually exclusive. Notice the sets do not overlap. They exclude one another. These two sets, however, are called inclusive. These are very important words. Make sure you understand those. When there's an overlap, they're inclusive. Okay, try this one out. Oh no, actually, let's look at this one. This one lists a bunch of students and it says they're taking different classes. So if you put the people in the right places, it looks like this. You have these people taking S, which is to Spanish, and then this circle is environmental science, I think, and then you have people taking geography, and then there's a person taking both. Anyway, that's the setup of that. So of course, when we do Venn diagrams, we can always list all the things and list them in there like we did in the previous question. However, it's often easier to, rather than listing all the things in the sets, to assign a number to them. So we have 2 things there, 2. We have 3 things there, 3. Because often these can become kind of tedious. The numbers can be quite big. So that's an important thing about Venn diagrams. We often see them like this, just with the number of items. Okay, so looking at that, try to answer these 4 questions. Okay, here are the answers. Check your work, and yeah, just take a look. If you see the diagram, I think you'll understand where these numbers came from. Okay, let's look at another example. We have a normal deck of cards, and we're looking for drawing 1 card, and we're trying to see if the probability, what's the probability of getting an ace or a king? So here's the aces, here's the kings. The probability of getting an ace is these 4 cards out of 52, and the probability of getting a king is 4 cards out of 52 also. So the probability of ace or king is just adding them up. So 4 and 4, 8, so there's 8 cards out of 52. Okay, and that reduces to 2/13. So this can be represented in a Venn diagram as well. We have our universal set, 52 cards. Here's aces, there are 4 of them. Here's kings, there are 4 of them. There is no overlap because a card cannot be an ace or a king. So these are mutually exclusive. There's 44 other cards out there because there's 8 here. And again, mutually exclusive. And we can see here clearly 8 out of 52. Now let's change it around a little bit. What's the probability of getting a queen or a diamond? Here's our queens, 4 of them. Here's our diamonds, 13 of them. So that means the probability would be 4 plus 13, right? Well, wrong, because there's an overlap here. So the queen, if you're counting this 13, the queen's counted as part of that group, and it's also counted as part of this group of 4. So the queen has been counted twice. So what we have to do is subtract that extra count. So minus 1 out of 52. So our probability of getting a queen or a diamond is actually 16 out of 52. So if you count these up and don't count that twice, you'll get 16. All right, as a Venn diagram, we can look at it like this. So we have, there's our 52 cards, there's our queens, there's our diamonds, there's 1 overlapping, the queen of diamonds. That means there's 3 that are just queens that are not diamonds, and there are 12 other diamonds, and there's the queen of diamonds. So you can see 36 there, and when we're looking for queen or diamond, we're looking for everything in here, so that's actually the union, and that adds up to 16. All right, so that matches our 16 there. Okay, these are inclusive, there's an overlap. Take a look at this one. Let's see what you get for probability of K intersection A. This was kind of a trick question, because there's our kids, there's our adults, there's no intersection. In this case, when you're looking for the intersection, well, there is no intersection. A kid cannot be an adult at the same time. So 0, our answer to that is 0. But this is a simple idea, but also important. Therefore, if you calculate an intersection is 0, you can say these must be mutually exclusive since the intersection is 0. So sometimes we don't have the diagram, we just have numbers and we calculate it. And if we ever get this result of intersection being 0, we can say they are mutually exclusive. Okay, try this one out. Here's a Venn diagram. Please add set C to this Venn diagram. Okay, so here it is with set C added. There's an overlap. Hopefully you got the same thing. And now try these problems. So we have that diagram. Try to answer B, C, and D. Here's the answer for B and C. Check those out carefully. Here's the answer for D. Okay, TOK question for you. I think this is important. Take a look at this and let's see if you can choose the choice that makes sense to you in this question. Okay, so now you are ready for video number 2 on this topic. It's called the addition rule. It's a very important follow-up on this one. Let's do it.